Welcome students. In the last lecture, we have seen hypothesis formulation and testing. In that hypothesis formulation and testing, we have seen what is null hypothesis and what is alternative hypothesis, just some introduction about the errors in hypothesis testing. Then we have seen Z test when sigma is known. When sigma is not known, we have done a T test also. In this lecture, we will go in detail about errors in hypothesis testing. We will take an example. This example is taken from this book, a famous book, Applied Statistics and Probability for Engineers, Douglas C. Montgomery and et al. It is very interesting book, so I will like to recommend this book for further reading after seeing this lecture. We are interested in burning rate of a solid propellant used to power aircrew escape system. Burning rate is a random variable that can be described by a probability distribution. Suppose our interest focus on mean burning rate. So, null hypothesis is mu equal to 50 centimeters per second, alternative hypothesis is mu not equal to 50 centimeters per second. You see that in the previous slides we have assumed mu equal to 50, but what is the basis for that 50? There are different possibilities how we can assume the value for our null hypothesis. One thing is the past experience or knowledge of the process or even from the previous test or experiments. Other possibility is from some theory or model regarding process under study. Even from external consideration such as design and engineering specifications or from contractual obligations, we can assume the value of null hypothesis. Suppose I know the, say I am following the say confidence interval method. So, I have found the lower limit is 48.5, upper limit is 51.5 when mu equal to 50 centimeters per second. If any mean value which is beyond this 51.5, which is beyond this 51.5, if the sample mean value is beyond 51.5, I will reject null hypothesis. At the same time, if it is below less than 48.5, again I will reject null hypothesis. So, what is happening? Decision criteria for testing H naught mu equal to 50 centimeter per second versus H1 mu not equal to 50 centimeter per second. So, in this example, we have taken the sample size is 10 and the population standard deviation is 2.5. So, by using the previous example, I will explain what is the meaning of this type 1 error. See, the true mean burning rate of the propellant could be equal to 50 centimeter per second. However, randomly selected propellant specimens that are tested, we could observe a value of test statistics x bar that falls into the critical region, rejection region. What is the rejection region? Below the lower limit, above the upper limit. So, if our x bar is lying on the rejection region, we will reject null hypothesis. If the x bar is lying on the acceptance region, we will accept null hypothesis. So, we will go to the next point. We would then reject null hypothesis H naught if in favor of alternative H1, in fact H naught is really true. So, this type of wrong conclusion is called type 1 error. What is the meaning of type 1 error? Even though the null hypothesis is true, but the x bar value lying on the rejection side, we have rejected null hypothesis. This is called type 1 error or incorrect rejection. You see, for example, in this slide, you see that there are two normal distribution, one is on left hand side, another one is right hand side. So, what will happen? This is a one tail test. For this value which is in the red portions, sometime the value of x bar may lie on the right hand side, that is in the red regions. We will reject null hypothesis even though the mu value is same. For example, in this case mu value is 50. For example, this normal distribution, the mu equal to 50. So, what is the meaning of type 1 error? Rejecting the null hypothesis H naught when it is true is defined as the type 1 error. So, what will happen? Actually, the null hypothesis is true because the sample was randomly selected, the value of x bar is falling on the rejection region, we have rejected a null hypothesis, but it is not correct. So, it is incorrect rejection. So, this is called type 1 error. Now, we will explain what is the meaning of type 2 error. Now, suppose the true mean burning rate is different from 50 centimeter per second, yet the sample mean x bar fall in the acceptance region. What will happen this? Now, the null hypothesis is not true, but the sample mean is following in the acceptance region. In this case, we would fail to reject H naught when it is false. So, what is happening? The H naught is false, but still we have accepted our H naught. So, it is false acceptance. So, this type of wrong conclusion is called type 2 error. So, I am saying what do you mean by type 1, type 2 error? See, the type 1 error is incorrect rejection, type 2 error is false acceptance. You see this situation, there are two normal distribution. One is we have seen this is 50, say it is 52. Now, what has happened? There are two populations which are overlapped. My concern is about the population whose mean is 50, but there is another population whose mean is 52 which are overlapping. So, what will happen? This much regions is not belongs to that light green one, it is not belongs to this population. So, this region is belongs to population whose mean is 52. Just because of it is lying on acceptance side of this population where the mean is 50, we have falsely accepted. So, it is called type 2 error. So, failing to reject null hypothesis when it is a false is defined as the type 2 error. You see the type 1, type 2 error. See, the H naught is correct, but we have rejected. So, this is your incorrect rejection alpha. The H naught is incorrect, but we have accepted, this is a type 1 error. So, that is a false acceptance. This we have seen previously also, the same table. Now, we will see how to calculate type 1 error and type 2 error. First, we will go with type 1 error. In the propellant burning rate example, a type 1 error will occur when either the sample mean is greater than 51.5 or sample mean is less than 48.5, when the true mean burning rate is mu equal to 50 centimeters per second. Suppose the standard deviation of the burning rate is, that is a sigma, is 2.5 centimeter per second and n equal to 10. So, the probability distribution mu equal to 50, the standard error, actually standard error is your sigma by root n, that value standard error is 0.759. So, what is the value of the type 1 error is when the probability of x bar less than or equal to 48.5 when true mean is 50 plus when the x bar is greater than 51.5 when true mean equal to 50. You see that? You see in the left hand side it is a 48.5. When the sample mean is, what is the probability of sample mean to lie below 48.5 plus what is the probability of that sample mean to lie above 51.5, when you add that, that corresponding probability is nothing but your type 1 error. You see that we got alpha by 2 0.0288. Similarly, on the right hand side we will see how this has come. Using Python, actually I have pasted the print screen of the Python after running. First, for finding the type 1 error, we will define a function. So, that function I am going to call it as DEF z underscore value x comma mu comma SEM, standard error of mean. You see that whenever we define a function, there should be a colon. So, first I am finding z value is x minus mu by standard error. If the z value is less than 0, that means if the value of it will be like this, if the z value is on the negative side, simply the p value is nothing but the cumulative distribution function of z. So, when you type alpha equal to alpha, just I am naming, equal to stats.norm.cdf z, you will get alpha value. Suppose if the z values greater than 0, we have to find out the right side area. So, if you want to know the right side area, the whole area has to be subtracted from 1. So, that we will get the right side area, else colon alpha equal to 1 minus stats.norm.cdf z. So, print alpha. So, calculating alpha for different value of x, mu and standard error of mean. You see, first I will find out the left side area. So, when area, suppose this is x value is 48.5, what will be the area? So, x is 48.5, mu, this is 0 for standard normal distribution, but we at present we are taking mu equal to 50, because after converting to z scale it will become 0. Standard error of the mean is sigma by root is 0.759. Now, we will call that function which we have defined. So, z value, so we have to give the value of x, because that function is defined 48.5, mu is 50, standard error of the mean. So, the left side area will get 0.0287, this value is given left side also, see that 0.0288, right. Now, we have to find out the right side area. Actually, this is alpha by 2 value, whatever value which we got it, this value is alpha by 2. If you put the upper value, that is 51.5 alpha by 2. So, if you replace instead of 48.5, if you put 51.5 here, when you replace this x and when you replace 51.5, what will happen? The z value will be positive. If the z value is positive, this command will be executed. So, if you want, first they will find this left side area, then from 1 the left side area will be subtracted, then you will get the right side area. So, you will get another 0.0287. When you add this 0.0287 plus 0.0287, you will get the alpha value. So, that alpha is 0.057, this is your value of alpha error, type 1 error. So, what is the meaning of this type 1 error? This implies that 5.7% of all random samples would lead to rejection of null hypothesis, that is H naught when mu equal to 50 centimeters per second. So, there is a possibility of rejecting true null hypothesis is 5.7%. So, we can reduce the type 1 error. One possibility is by widening the acceptance region. What is the widening the acceptance region? If you make critical value 48 and 52, what will happen? What is the widening of this acceptance region is? Suppose this is currently this one. So, when you increase, now it is 51.5. So, now you make it this right hand side 52, left hand side 48. So, what is happening? The acceptance region is widened. Yeah, you see that lower side on 48, upper side 52. So, what is area cutting? 0.00567 plus 0.00567. When you add it, it will become 0.0114. So, what is happening? The type 1 error can be reduced by increasing the acceptance region. That is one possibility. Another possibility is if you increase the sample size. The previous problem we have taken sample size is 10. Now, from 10 if you increase 16, what is happening? The value of alpha is decreasing. That means, the alpha is decreasing means we are more accurate in making decision. That is, the possibility of incorrect rejection is reduced. Next we will go to type 2 error. First I will explain what is a type 2 error, and I will take 3 examples to calculate the value of type 2 error. In the previous example, what has happened? There are two population which are overlapped. So, this is 50, this is 52. The rejection region, this is this much when the population mean is 50. There is another population whose mean is 52, which is overlapping. So, this overlapping region is that pink one, because the pink portion is lying on acceptance side, we have falsely accepted, assuming that that region has come from the population mean whose value is 50. So, it is a false acceptance, right. So, this pink region is nothing but the value of your type 2 error. Suppose how to find out this type 2 error? See, type 2 error will be committed if the sample mean x bar falls between 48.5 and 51.5 critical region when mu equal to 52. You see that it is a 52, not mu equal to 50. When I say 52, that population is nothing to do when the mean equal to 52 population, because it is something other population, but it is lying on the acceptance side. So, I am accepting, falsely I have accepted. So, that is our type 2 error. So, what is the possibility? So, this is our 51.5. So, what is happening? There are two two population is overlapped. So, this is our original mu equal to 50. So, this region is 51.5, this left hand side is what is that value 48.5. This is for my assumed hypothesis value and mu equal to 50. But actually what has happened, there is another population whose mean is 52. So, I am extending this. So, this much portion is not really belongs to the first one, but lying on the acceptance side. So, this much portions I have falsely accepted. So, this portion is called beta, this portion is called alpha. So, we have to find out the value of beta, and one more thing, the value of alpha plus beta is not equal to 1, you should be very careful. So, what is happening? This is 51.5. So, this also 51.5 because this condition is same. Now, for this population, that is which is on the below, we have to find out the left side area. Generally, how will you do that? First you have to find out the z value. Z value is x minus mu by sigma. So, 51.5 minus 52 divided by sigma by root n. So, what will happen? For this region, when z is below the left hand side, the corresponding value is your type 2 error. See that I have done that also. So, I am calling it beta stats dot norm dot CDF cumulative distribution function. So, my x value is 51.5 minus my true mean is 52 divided by sigma by root n is 0.7. So, that beta value is 0.263. Okay. So, this 0.263 is nothing but this value 0.263, this is 0.2264. So, this is that pink region area is this one. Just I have given an explanation, the code of also Python is given how to find out. Now, you see that now mu equal to 50.5. What will happen again between the true mean and assumed mean, the difference is becoming less. So, if I put the true mean is 50.5, you see that I have changed there 52, here I have changed it 50.5. So, again beta equal to stats dot norm dot CDF 51.5, this is nothing but x bar minus mu divided by sigma by root n, that value is 89. You see that the value of beta has increased. So, one point at present you have to remember, when the difference is decreasing between your assumed mean and the true mean, the type 2 error is increasing. We can say one example, suppose there are two products, one is original, another one is duplicate. Both are looking similar color wise, texture wise, quality wise. There are more possibility for committing type 2 error whenever the difference between original and duplicate of product is very less. The same way, whenever the mean, the population which you assumed, and the true mean, the difference is less, there is more possibility of committing type 2 error. That I will explain. You see this one? Again, when the mean is 50.5, there are more pink region, that is there is more type 2 error. Okay. So, the point is, when the distance between your assumed mean and the true mean is decreasing, there are more possibility of committing type 2 error. Okay. Now, we will see computing of this type 2 error, already I have explained. So, computing the probability of type 2 error may be the most difficult concept. If you are doing it with the help of statistical table, it will take more time, that is why we go for Python, that will solve our problem very quickly. Okay. So, this area we have found already. Okay. Now, look at this table. Acceptance region is there, sample size is there. You see that for the same sample size, when you increase the acceptance region, what is happening? The alpha is decreasing. Sample size is same, you are widening the acceptance region. So, the alpha is decreasing. When alpha is decreasing, you see what is happening? The beta is increasing. So, the relation between alpha and beta is when you decrease alpha, beta will increase. It is like this. As I told you previously, there are two normal distribution. This is your rejection region. There is another normal distribution. This is mu equal to 50. This is 52. So, this side portions. So, this is your alpha, this side portion is beta. I will change the color. Okay. So, this portion, the green portion is nothing but your type 2 error. That red portion is your type 1 error, alpha and beta. So, what is happening? Suppose assume that I am keeping in that line where there is intersections there, I am keeping a pen like this. If I move towards right hand side, what will happen? Alpha will decrease. So, when alpha is decreasing, what is happening to beta? Beta value is increasing. Suppose I am keeping this pen, I am moving towards left hand side, what will happen? Beta will decrease, but alpha will increase. So, that is explained with the help of this table. So, the relationship between alpha and beta is inverse. Apart from this, you go to the last column, the mu equal to 52. Again, I am the mu 50.5. Suppose the difference is decreasing. What is happening? The value of beta is increasing. Okay. That is one point. Now, we will look at the another point. Suppose when you increase the sample size, you keep the acceptance region as it is, you increase the sample size 10 to 16, you see that? When you go to 10 to 16, you see here 48.5, 51.5, sample size is 10, alpha is 0.05. For the same region, when you increase, you compare this, I will go to, say I am comparing this. Acceptance region is same, but I have increased my sample size, the alpha value is decreasing. See, initially alpha value is 0.05, now it is 0.01. Look at this beta also. The value of beta also, you see initially it is a 0.26, now it is 0.21. So, what the point we are learning from here is, when you keep acceptance region as the constant one, when you increase the sample size, both value of alpha and beta will decrease. Okay. That is a point here. Let us see this. For constant n, when you increase the acceptance region, alpha is decreasing. When the alpha is decreasing, beta value is increasing. Second point, increasing n can decrease both type of error, that is type 1 and type 2. That is the learning from this slide. Type 1 and type 2 errors having an inverse relationship. If you reduce the probability of one error, the other one increases, so that everything else unchanged. So, that is the relation between alpha and beta. Remember, alpha plus beta is not equal to 1. Now, let us see factors affecting type 2 error. The true value of population parameter, beta increases when the difference between, this point already I told you, the difference between hypothesized parameter and its true values decreasing. Significance level alpha increases when beta decreases. Population standard deviation sigma increases when beta increases. Sample size beta increases when n decreases. That is the relation between your different element of your type 2 error. Okay. How to choose the between type 1 and type 2 error? The choice depends upon the cost of error. So, the first point is choose smaller type 1 error when the cost of rejecting the maintained hypothesis high. For example, in a criminal trial, convicting an innocent person is very costly mistake. So, that time the value of alpha should be very less. Choosing a larger type 1 error when you have an interest in changing the status quo. So, what will happen if you are willing to change the status quo? If you increase the alpha value, obviously there is a more chances for rejection region, your hypothesis get rejected, that is the status quo is getting rejected. We will take another problem to find out type 2 error. So, I am assuming mu equal to 8.3, alternative hypothesis mu less than 8.3, it is a left tail test. Determine the probability of type 2 error if the true mean is 7.4 at 5% significance level when sigma is 3.1 and n equal to 60. See that I have drawn this one. My assumed mean is 8.3. The question is asked, if the true mean is 7.4, what is the value of beta? You see that if any portions which are going on left hand side, I will reject it. So, this side I will reject it, but the right hand side I will accept it. Accept. But what is happening? The true mean is 7.4. It is lying on acceptance side of where the mu equal to 8.3. Actually, I have to reject this since it is lying on the acceptance region. So, this much portion I have falsely accepted. So, that beta value is nothing but your type 2 error. See that the value of C is constant for this population and this population. So, we have to find out this right side area. So, for this purpose I have developed a function, because this function is very useful. First you let us understand. So, I am going to define a function, I am going to call it as a type underscore 2. So, what are the parameter which I am going to take? Mu 1 my assumed mean, mu 2 true mean, sigma population standard deviation, n sample size, alpha significance level, colon. So, for example, the first one which is in the topper one, the normal distribution, I am finding out what is the z value in this location, what is the z value. I know what is the alpha value. So, z equal to stats.norm.ppf alpha value. If I substitute, what will happen? I will get the value of z. If I know the value of z, I can find out x bar. How I can find out? Because z equal to in this relationship, if I know z value, I can find out x bar. So, x bar is when you mu multiplied by mu plus, when you bring this left hand side, sigma z multiplied by sigma by root n, that is written x bar equal to mu 1 plus z star sigma divided by np, because from that is kind of numpy dot square root of n. So, I will get x bar. This is the value of z. Now, I have to find out the z2. The z2, this what will be the z2 this x bar, this x bar, this value is x bar. So, corresponding normalized scale is z2. So, what will happen? Z2 is x bar minus mu 2, that is for the from this population what is the mean, that is a 7.4, x bar minus mu 2 divided by sigma divided by np dot square root n. You see the condition, if mu 1 is greater than mu 2, what is the mu 1? Mu 1 is now 8.3, this is 7.4. In this case, yes, mu 1 is greater than mu 2. What will happen? I will get the positive z value. If the z is positive, if I want to know the p value, from 1 I have to subtract it. So, if the z value is positive, the beta equal to 1 minus stats.norm.cdf z2. If z value is negative, just finding the left side value, beta equal to stats.norm.cdf z2 print beta. So, when you type this in Python, type underscore, now we have to give this value of mu 1. Suppose what I am going to do, I am going to find out the beta value. The mu 1 is the assumed mean 8.3, mu 2 is true mean 7.4, sigma is 3.1, sample size is 60, alpha equal to 0.05. So, now what will happen here? If it is a positive value, the corresponding probability is 0.2729, that is why that value, yes, this 0.2729. So, the right side beta value is 0.2729. So, when we will commit to type 2 error? an error will be made when z value is greater than. So, now here the corresponding z value is minus 1.6 power 5. Whenever you crossing minus 1.645 on the right hand side, then you will accept that is nothing but your value of type 2 error. Okay. I will take another example, solving for type 2 error. One more example, mu equal to 12, mu less than equal to 12. We know that x bar equal to mu z sigma by root n. So, here assumed mean is 12, z value is, because the left side you will get when alpha equal to 0.05, corresponding zc is minus 1.645, sigma value is given, the x bar is 11.979. If the value of x bar is below 11.97, I will reject it. If the x bar is above 11.979, I will accept my null hypothesis. Now, look at this graph. You see that my assumed mean is 12. Suppose my true mean is 11.979. What will be the value of type 2 error? You see that when alpha equal to 0.05 minus 1.645, I know that. So, what will happen if the true mean is 11.979, what will happen? Z value will be x bar minus mu. So, 11.979 minus 12 sigma by root n, right, we will get z value. So, corresponding right hand side area is my type 2 error. So, beta equal to 0.8023. Okay. I have done some code for this. So, type 2 error. So, 12 is, what is that? My assumed mean, 11.99 is my true mean, this is my standard deviation sigma value, this is my n, this is my alpha. So, it is 80, that is why this much area. So, what we are getting? We are getting 8079, 80 approximately 80 percentage. I will go to see another problem. The true mean is 11.96, little far away from the 12. What is that? The true mean is gone towards left hand side. Now, what has happened to the value of beta? So, this portion is my beta, type 2 error. So, by use already we have developed a function for that. We will substitute this 12, 11.96, 0.1, 60, 0.05. So, what is happening? The value of beta is becoming very less. Again I am stressing this point. If the difference is bigger, the value of beta is very less. If the difference is closer, the value of beta is very high. Now, hypothesis testing and decision making. We have illustrated hypothesis testing applications. Now, let us see what is the application of this type 2 error. We have illustrated hypothesis testing applications referred to as a significance test. In the test, we have compared the p value to a controlled probability of type 1 error alpha, which is called the level of significance for the test. What we have done? To accept or reject null hypothesis, we have considered the p value that is compared with alpha. If the p value is smaller than the alpha, we have rejected it. The p value is greater than alpha, we have accepted it. So, we will go to next point. With the significance test, we controlled the probability of making type 1 error, but not the type 2 error. We recommended the conclusion, do not reject H naught. Actually, we have to use accept H naught, but very cautiously we have used do not reject H naught rather than accept H naught, because the latter puts us at risk of making type 2 error. Why we are not accepting? There is no proof that the value which I have assumed in a null hypothesis is correct. So, that is why we are saying do not reject it. Now, in this example, what we are going to do? What should be the value of your null hypothesis, so that the something called the power of test can be improved. We will see the definition of power of test. Okay. With the conclusion do not reject H naught, the statistical evidence is considered inconclusive. You are not able to say anything. Usually, this is an indication to postpone a decision until the further research and testing is undertaken. But in many decision making situations, the decision maker may want and in some cases may be forced to take action both the conclusion do not reject or the conclusion reject H naught. In such situation, it is recommended that a hypothesis testing procedure be extended to include consideration of making type 2 error. So, what we are going to say, whenever we do the hypothesis testing, we have to see the possibility of committing type 2 error also. That I will show you with the help of an example. That point is called power of test. Okay. Suppose there is a restaurant is there. Suppose in the restaurant, when you order some dosa, when you order some coffee or soup, many times it will take different, some time because they have to prepare it. Okay. Assume that the owner of that restaurant has the target of service goal of 12 minutes or less, whether it can be achieved or not. So, what is the different possibility of committing type 2 error if you assume mu equal to 12? We will see the problem in detail. Okay. The mean response time for a random sample of 40 food order is say 13.25 minutes. The population standard deviation is believed to be 3.2 minutes. The restaurant owner wants to perform a hypothesis test with alpha equal to 5% significance level to determine whether the service goal of 12 minutes or less is being achieved. Okay. Now, what is happening? First we have to start null hypothesis. So, null hypothesis is the status quo. The status quo is mu less than or equal to 12. Alternate hypothesis is mu greater than or equal to 12. So, what will happen? What kind of test this is? This is right tail test. So, this value is 12. If anything goes this side, I will reject it. So, when alpha equal to 0.05, so the corresponding value is 1.645. If any value z value goes beyond 1.645, I will reject it. So, we will substitute this value into our z formula. So, z equal to x bar minus 12, 3.2 root of 40. If it is greater than 1.645, I will reject it. So, from this relationship, I will bring the value of x bar. Okay, we are finding the value of x bar, that is a 12.83. So, what will happen? We will accept H naught when the value of x bar is 12.83. So, this value is 12.83. If anything value goes that side, we will accept H naught. If anything goes below this, we will reject it. So, what will happen here? In this, we assumed, you said, we have assumed mu less than or equal to 12, H1 mu greater than 12. Now, the question is what is the logic behind this 12? Okay. So, what I am going to do, instead of this 12, I am going to supply different values of this mu value. Say I am going to supply 14, 13.6, 13.2, 12.00. So, value of mu. So, z is 12.8383 minus mu divided by 3.240. In this z formula, when you substitute the value of mu 14, this is the z value. So, when the z value is minus 2.31, what is the value of type 2 error? 0.01. So, 1 minus beta. So, this 1 minus beta is nothing but power of a test. Power of a test is rejecting a null hypothesis when it should be rejected. Okay. So, now instead of 14, if I make 13, so again the z value is minus 1.52. So, corresponding beta value is 0.64. You see that when the difference is becoming closer to 12, what is happening? You see that the value of beta is increasing. Whenever value of beta is increasing, the power of test is decreasing. Okay. So, how we got this 0.0104? I have done in the next slide. See, I am calling that function which I have previously used. So, type underscore 2, if true mean is 14, assumed mean is 12, sigma is 3.2, n equal to 40, alpha equal to 0.05. So, my beta is 0.01. Okay. This is for this is 14. Suppose if it is a 13.6, it is right, I am substituting 13.6, all other value, my beta value is 0.06. So, that is this value. So, when it is 13.2, what is the beta value? So, substituting 13.2, the beta value is 0.23, 0.23. If it is 12.8, again beta value is 0.5 and so on. So, if I plot this, okay, now I will come to, before plotting I will define what is this power of test. The probability of correctly rejecting null hypothesis when it is false is called the power of test. For any particular value of mu, this is mu, the power is 1 minus beta, you call it as capital B, that is convenient. So, we can show graphically the power associated with each value of mu, such graph is called power curve. So, the application of power curve, first I will explain what is the element in this power curve. Here in the x axis the true mean which I have assumed, in the y axis the value of is 1 minus beta, probability of currently rejecting null hypothesis. What is happening when the difference is increasing between true mean even your assumed mean, there is a more chances you will correctly reject your null hypothesis. So, this power of test says what should be the value of mu. See that when if you assume mu equal to 12, power is less. When the power is, when you assume mu equal to 14.5, this power is more. So, this power curve is helping us to decide what is the possibility of committing type 2 error. At the same time, how much value of null hypothesis we can have, so that we can improve our power of a test, otherwise we can decrease the beta. Dear students, in this lecture we have seen different types of error while doing hypothesis testing. We have taken one practical example. I have explained what is the meaning of type 1 error and type 2 error, and also we have calculated value of type 1 error and type 2 error. At the end we have seen power of a hypothesis testing, we call it as a power curve. So, what we have done, we have suggested what is the possible value of mu and corresponding beta value or a corresponding power of a test. So, with that we will conclude in this lecture. In the next lecture we will go for 2 sample hypothesis testing. Thank you very much.